is a function that when you plug 0 in, what do you get? Positive 1. And when you plug negative 1 in, what do you get? Some negative number, right? Something down here. I don't know what it is, and I don't care. I could have got my calculator out and figured this out, but I go between negative 1 and 0. What does my function do? It goes from a negative to a positive, which means it must do what? Somewhere in between there, must cross through the x-axis, right? Yes? You don't follow? So this is the intermediate value theorem. We did talk about this, so I'm hoping this kind of rings a bell. What we're trying to show here is that our function went from negative to positive. It changed signs. So if it changed signs, it has to go through 0. So do you all agree that I've shown that there's a solution? Somewhere in there, I have an x-intercept. So somewhere in here, this function is equal to 0. Yes? Have I shown there's only one x-intercept? No, because it could do this, right? It could do something like that, and it could have 2 in there, right? I don't know. I just know there's at least one, because it I have to go from here to here. So I don't know what it does, right? So have I done what I'm supposed to show? Show it has exactly one? I haven't done that, have I? No. So how would I do that? Ready? This is the big didn't think I could, not something you normally think of. What I'm going to do now is I'm going to take this function and I'm going to take its derivative. Why are you doing that, Robert? I guess, don't they say when you talk about yourself in third person, that means you're going insane? Yes, I guess I'm going insane. So what's the derivative of this? 2. What's the derivative of cosine x? Minus sine x. Okay. Now, this is what you have to put together. This derivative is always positive or negative. No matter what x you ever plug in, this will always be positive or negative. You tell me. What? Positive? Why? This is between negative 1 and 1. I mean, yeah, negative 1 and 1. That's the biggest this could be was 1, right? And the smallest would be negative 1. So what if it's 1? What is this? 2 minus 1? That's still positive, right? What if it's negative 1? What's 2 minus negative 1? That's 2 plus 1, right? That's 3. Do y'all see that this will never be negative? Yeah? That will never be negative. So I'm going to put here this is greater than 0. And this is leading us into the next section. Think about it. What this is saying to you is that no matter where you are on this graph, right? The derivative is the slope of the tangent line, right? And it's saying no matter where you are on the graph, that derivative is positive, which means the slope of the tangent line is positive. So could it do this? Could that be possible that I go through here, go up, and then tangent lines come back down and then go back up? Is that even possible for my graph to turn back like that? No, because the slope of the tangent line has to be positive. See, the fact that the derivative is positive tells you that as you move from left to right, your graph must always be going up. Can't turn back. That's a big thing here. I mean, this is a big okay. We can use the derivative to tell us something about what the graph looks like, right? So I use the intermediate value theorem to show you there's at least one answer. Between negative 1 and 0, there's at least one answer. Then I use the fact that the derivative is positive to show you that there's only one. All right? All right, I'm not asking you to do this. I wanted to just show it to you. All right? The next section that we're going to get into here, and hopefully in the next 5-10 minutes, is about how does the derivative impact the shape of the graph. And that's, so we're going to do a lot more of this. This was just kind of leading you into it. All right, you want to talk about the car problem? You want to resolve that? Do you remember that? The two cars that were racing? Do you all remember that or no? Okay, so I'll restate what it was. We had two cars, car A and then car B, and then they started at the same, they raced, they got to the finish line, and they tied, right? It was an exact tie, right? And my question to you was, is there a point in time, Somewhere in the race, is there a speed that both cars had to be going at that exact same time? Is it guaranteed? And there was kind of conflicting ideas in the class. A lot of you thought no, that it doesn't have to be, there doesn't have to be a point in time where they're both going the same speed. And we debated it, and I said I would prove it to you, right? So you ready to see the proof? I mean, I had to do this proof when I was a junior in college, I think. I had to do this proof, and it was in a class called analysis. So it's not something that a Cal 1 student would ever be asked to do, all right? Because this proof is going to look very unnatural. Like, you're not going to have thought of this. You know what I mean? Like, most people won't come up with this on their own. So the most important thing for you is to see if you follow it, all right? See if you can follow the logic of it. Are there any math majors? I don't think there's math majors in here, right? No math majors? Yeah, okay. This is what math majors have to do. All right, here's what I'm going to do. First thing I'm going to do is I'm going to start by just drawing a graph, all right? And this is going to be time, and this is going to be distance here, all right? And I'm going to graph both cars one at a time. So I'm going to graph the first function. I'm going to do in blue. Let's do it in red. Will be the A car. All right. All right. So the A car. Do you agree at time equals 0, it hasn't gone anywhere? Beginning of the race, right? And then it has some path, right? Time goes, it starts moving. It has a distance that it's traveled. And no matter what the race looks like, whatever the car does, at the end of the race, okay, that's the time where they finish together, right? Whatever that is, I don't care what it is. Let's just call that, I don't know. Well, let's just leave it, all right? That's where that car ends, right? And then this distance it travels is the finish line, right? So this is the time they finish, and this is the finish line. Got it? Okay, car B in blue starts at the same point, doesn't it? Same point in time. And the only other thing that has to happen is it has to end here at the same time it has to finish, yes? But the path can look like anything, right? As long as it's continuous, because the car doesn't vanish, right? Go through some portal and then come back, and right? So as long as it's continuous, so however I draw it, it doesn't matter, okay? It doesn't matter how I draw it. I'm going to call the first red curve, I'm going to call it f of x. And I'm going to call the blue curve g of x. Let's call the point that they started, let's call that A. Let's call the point where they ended, let's call that B. All right? Everyone understand the geometry of this, or the setup here so far? Any questions about it? All right, what am I trying to prove to you? What am I trying to prove to you? That there's somewhere in this race, right? The same place, right? The same point in time. There's some point here where if I go to both the curves, what should be the same? The speeds, which means the slopes of the tangent lines, right? That's what I said. Is there a point in time in the race where both cars are going the same speed? So here's what I want to prove to you. I want to show this. There exists a point C, right? A point C somewhere in the interval AB, right? Not at the beginning of the race and not at the end of the race, somewhere in between. I want to show that there's some point such that what's true? The speed of the red one, right, is equal to the speed of the blue one, right? That means the derivative of the f function at C is equal to the derivative of the g function at C, right? Do you all agree this is the speed of car A at C? Do you all agree that this is the speed of car B at C? I need to somehow prove to you that this is true, okay? Are y'all happy with that? If I show this to you, will you be satisfied? If I can prove this to you? Okay, now I have to prove it. I haven't proven anything, right? But this is what I'm going to try and prove to you now. All right, so here's the way I'm going to do it. This is the very unnatural thing. I'm going to draw a new function. This is the part, this is the leap. This is the part that most people can't get. And I can't remember how long it took me to figure this out, all right? It took me a while, a couple of weeks, all right? So you have to create a new function. And so this new function that I'm going to create, what it's going to be, I'm going to call it m. I don't know why. I'm going to call it m of x. I call it anything I want. What it's going to be is the difference of these two functions. It's going to be the f of x take away the g of x. Now you're going to sit there and go, why are you doing that? That doesn't make any sense. Just do it and let's see what happens, all right? So all this function does is takes the red function and subtracts the blue one. So what can you tell me about the value of the functions at a? What is m at a? 0. Why? Because both the red and blue are the exact same value at a, right? So if you subtract the two, you get 0. Okay, so if I graph the m function at 0, it's here. All right, what can you tell me about the m function at b? Well, it's the f function at b minus the g function at b. So what's the difference of the functions at the end? 0 again, right? So this new function I have starts here and ends here. Yeah? And just geometrically, I don't really even care what m looks like, but do you agree that m has to be continuous? Like, I have to be able to draw this without picking up my pencil? So no matter what it does, who cares, all right? No matter what it does, there's m, right? So is m continuous? Is m continuous? Yes. On a closed interval, right? I'm going to use the mean value theorem now. So what is the slope of the secant line connecting the two? What's the slope of that line connecting the two endpoints? 0, right? The mean value theorem tells me that there exists a c in that interval AB such that, what does the mean value theorem say? The derivative of that function m at c must be equal to the slope of the secant line, right? The derivative of the function at some value in there must be equal to the slope of the secant line. What's the slope of the secant line? You just told me. 0, right? But that must be true, right? This new function is continuous and they're on a closed interval, so the mean value theorem should apply, which means that somewhere in between here and here, there's some value c that the slope of the tangent line will be parallel to the slope of the secant line. So the slope of the tangent line should be 0 somewhere in there, right? I still don't know where it is, but somewhere in there it should happen. Yes? I'm almost there. I'm like 2 lines away from proving it, even though it doesn't look like I have. So what is this? If I ask you to take derivative of m and plug in c, come over here and take the derivative of this. If I ask you to take derivative, you take derivative left side, that's the derivative, right? How do you take derivative of the right side? You have subtraction, right? Can you do them individually? Yes, right? So that would mean derivative of that, derivative of that. So the derivative of m at c is the same as saying f prime of c minus g prime of c must be 0, right? That's the derivative of m is this, and then when you plug c into it, plug c into this, you get that. Y'all agree with that line? Next line, I'm done. What am I going to do? Do y'all see what I'm going to do? Remember what I wanted to show you, right? I'm almost there. What do I do? Yeah, move this to the other side. Add g prime of x. And I'm done. We usually put a box when we're done, when we've shown what we wanted to show. So this says that there is some point C, right, in between A and B, where the two speeds are the same. All right, I just want to show that to you. Let's move on. Yes? The moral of the story for this problem is that that car problem, I think that's debatable. Like when you give that problem to people, they think about it, and then some people are like, no, there's no way that could happen. Other people are like, yeah, maybe it could happen. Sometimes we need the math, and I told you all this last class. Sometimes you have to things are counterintuitive. They don't go the way you think they were going to go. So we have to have some sort of system in place to get good answers. And math is that system. What is it that you're going to need to do on the test? For this section, the problems that I gave you for homework, number 9 and 10, that's what you need to be able to do, right? All right. I told you last class that section 4.2 was us taking a detour off the highway, right? Taking a little pit stop, mean value theorem. Now we're going to get back on the highway. Remember 4.1, we were trying to find the highest and lowest points on a graph? Highest and lowest points if the graph was on a closed interval. And we had this thing called the closed interval method, right? So, and that's on your test, right? On your exam, that's going to be on Thursday. You're going to have to do at least one of those problems. So now we're back on that highway. We're trying to find highest and lowest points on a graph, but we're no longer going to restrict it to a closed interval. So 4.3. Derivatives and the shapes of graphs. So we're now going to investigate further how the derivative can tell you about the shape of a graph, like what it looks like. The first note here is a definition. So I'm going to read the definition first, then we're going to look at it visually, because when you look at the definition, you're like, what? And then once you see it, you're like, oh, okay, that makes sense. All right, so look, this first note says this. If the derivative of a function is positive on some interval, so your derivative is positive, slope of tangent line is positive, right? Slope of tangent line is 0, slope of tangent line is negative, right? So if the slope of tangent line is positive on some interval, then the function must be increasing on that interval, which means your function has to be going up as you go from left to right. The function has to be going up. Does that seem reasonable to you? If the derivative is negative on some interval, then the function must be decreasing. That means it must be going down, right? And then if the derivative is 0 on some interval, then that means the function must be constant. It must be just flat line, right? So here's an example, okay? There's an example of an increasing function. When you go from left to right, it goes up. And you can see that if you go to any point on the graph, notice that the tangent line is always positive, right? I have green to represent positive, right? I have the computer calculating the derivative. It's always a positive number, and the graph is increasing. On the other hand, this is a decreasing graph. As you go from left to right, the graph goes down. You can see that the derivative there, the slope of tangent line, is always negative no matter where you are on that graph, right? And then finally, constant. If you have a constant function, then the derivative is always 0. See it moving along there? Is that a pretty straightforward, simple concept? Yes? Okay. So the derivative tells you about the shape of the graph, right? The derivative, if it's positive, tells you the graph goes up. If the derivative is negative, it goes down. If it's 0, it's constant. All right, here's a function. Is this function always increasing? No, it goes up and then down and then up, right? So what should we expect the derivative to do? Well, over here, the derivative should be positive, right? And then when we get to the top of this graph, it should be 0, right? Just for a moment, it's going to be 0. And then it's going to shift to be negative, right? The derivative will be negative. And then when we get to the bottom of this, the derivative will be 0. And then when we keep moving, the derivative will go back to positive, right? So you see how it switched? It went from positive to negative and then back to positive. So again, that derivative is telling you about the shape of the graph. So now we have what's called the first derivative test. So we define in 4.1, we defined what were called the critical numbers of a function. Do you all remember how to find the critical numbers of a function? What are they? Or what's 0? Where the derivative is 0, and also where the derivative does not exist. Anywhere the derivative is 0, and anywhere the derivative doesn't exist, it was called a critical number. All right? So this test says, look, hey, let's say you have found a critical number. Okay, so you've found where the derivative is 0 or doesn't exist, which is what we did in 4.1 already, right? So that's not a new concept. It says, okay, so let's say we found some critical numbers. This says if the derivative changes from positive to negative at that critical number, then the function must have a local maximum. Think about what that's saying. Let's say that you have a function, and at some point c, I tell you that that's a critical number. That means that the derivative is either positive, the derivative is either 0 there or the derivative doesn't exist there, right? And what if the function is increasing, right? The derivative on the left side of it, right? It goes from positive to negative. So I tell you over here the derivative is positive, but over here the derivative is negative. Do you all see that that would mean it would have to come up and then back down? And that would make that would force that to be a local maximum, wouldn't it? On the other hand, if the derivative changes from negative to positive at this point, it's got to be a local minimum, right? It's going to go down, then back up. So it'd be the opposite of this picture. It'd go like that, right? And then the third thing says, if it doesn't change, right? If the derivative doesn't change, if it goes from positive and stays positive, then you cannot be at a local maximum or a local minimum. Or if it stays negative, goes negative to negative, then it's not going to be a local max or min. So what we're looking for is a change in the derivative on each side of the critical number, right? On the left side, what we want to do is see what's the derivative doing here, and then we want to go over there and look at what's the derivative doing there. And if there's a change in sign, we're going to either have a local max or min. So here's an example. So if I move, well, first we should talk about what we have here. This point right here is called a what? Max. Is it the absolute max? Is it a local max? What is it? This is a local max. Do we have any other local maxes? These are arrows that goes forever. So do we have any other local maxes? No? Do we have any local mins? Yes. Right here? It's a local min, right? That's all we have, right? Just one local max, one local min. Let's look at what the derivative does to the left and right of these. So as I move from left to right, notice the derivative right now is positive, isn't it? It's positive. And then as I get to the top, the derivative is 0, and then it goes to negative. And I've left a green there to represent positive derivative, and then I'm leaving a red behind wherever the derivative is negative. So do you see? This is a critical number. To the left, the derivative was positive, and the right, it was negative, so that's a local max. What about right here? Doesn't it look like right here the derivative would be 0? Right? Doesn't that look like the derivative would be 0 there? But what does the derivative do on each side of it? Right now it's negative, right? The derivative is negative on the left side. What's it on the right side? Still negative, isn't it? So did the derivative change signs? Went from negative to negative. So we should not expect to see a local max or min here. And then finally, when we get over here, it's negative derivative, right? Negative, negative, negative. And then turns and now becomes positive. And so you went from a negative derivative, right, to a positive derivative, which means that you're at a local max. Local min. That's the first derivative test. So let's do an example. Does the idea make sense? I mean, like there's nothing crazy about that idea? The big thing for us is how do we do it? Like how do we implement this idea into a problem? So let's go back and let's go and do a problem. Let's keep it kind of straightforward. We'll do a polynomial. So let's say I give you that f of x is equal to negative 2x cubed. Let's go plus 3x squared plus 36x. And here's what I want from this, all right? I want you to find, part A, find where the function, I'm going to put an arrow next to it. What do you think I mean by that? I'm asking you to find where the function is doing what? Increasing. That means, for me, that means function is increasing. Tell me where this graph is going up. Then I want you to tell me where this graph is going down. And finally, I want you to find any local max and local minimums. So I want you to find any like peaks and valleys to this function. Understand what the question's asking? How do you think I'm going to go about answering the first one part? If I'm asking where the graph's going up, what does that mean to you? Where what? What's positive? I'm asking where what is positive? The derivative. So this is asking you, where's the function going up corresponds to where's the derivative positive. Where's the function going down corresponds to where's the derivative negative, right? Then the local maxes and mins are going to be where we see changes in that derivative. Anywhere we see a change is going to give us either a local max or a local min. Okay, so here's the procedure, all right? The first thing I'm going to do this, first thing I'm going to do is I'm going to find the derivative. I'm just going to take derivative, all right? First step, I'm going to take derivative of this function. What's derivative of that? This should be pretty okay, right? Negative 6x squared plus 6x plus 36. Right, that's my derivative. Now I want to know where this is positive and I want to know where it's negative, right? So what I'm going to do next is I'm going to find the critical numbers. I want to figure out where this is 0 and where it's undefined. So the critical numbers, I need to figure out where the derivative is 0, right? And then the other thing I need to do is figure out where the derivative does not exist. This is very similar to section 4.1, right? This is exactly what we did in 4.1. Okay, so there's nothing new here. Let's do the right one first. Doesn't exist. Does that derivative ever have a problem? Are there any issues with that ever? No, because it's a quadratic, right? So there's no domain issues. That's a well-behaved function. It's a polynomial. So the derivative is never not going to exist. So I'm not worried about that. Now, what about where the derivative is 0? That I do have to worry about because this is a quadratic equation, isn't it? Or it's a quadratic function. When I set it equal to 0, I need to solve that. So I could use the quadratic formula, couldn't I, right? But I think I'm going to try factoring it because I'm pretty sure it's going to factor. The problem came out of the book, so I'm pretty confident that it's going to factor. I'm going to pull a negative 6 out of everything first. Do you all agree that's what would happen if I factor a negative 6 out? Divide both sides by negative 6, just to get rid of it. All right, you can divide both sides by negative 6. And it's gone. Right, because 0 divided by negative 6 is still 0. And then that does factor. Can someone tell me what the factoring of this is? X what? Plus 2 minus 3. Plus 2 minus 3. And that means we have two solutions, don't we? We have x is negative 2 and x is 3. So remember, to be a critical number, you have to be in the domain of the original function. Was there any domain issues up here? No, it's polynomials. So these are critical numbers. We don't have to throw anything out. Okay, so what I've done right now is I've said, all right, I have this function. I have found its critical numbers. And so now what I want to know is what's going on with the derivative, right, around these critical numbers. Like, is the derivative positive or negative to the left and right of these critical numbers? So the way I'm going to do that is this step. And this is where things are very different than 4.1. See, we don't have a closed interval anymore. So I'm going to show you my method of doing this, all right? And it's going to be different than probably a tutor will show you. They'll probably show you something called a sign chart, something like that. I learned that as well when I was a Cal 1 student, and then later on when I understood it more, I decided I would just start doing it a different way. It gets you to the same answer. I think it makes sense. So let's see if you like this or not. So what I like to do at this point, I'm going to erase this. What I like to do now is I like to draw a number line. Okay, I'm going to draw a number line. This would be, I guess the derivative was the first step. Second step was finding the critical numbers. The third step here is we're going to do a number line. Okay, so on your number line, we're going to plot our two critical numbers. And it doesn't matter, it doesn't have to be like drawn perfectly. You just need to make sure you get them in order from left to right. What I know is that my function is doing something interesting at these 2 points, right? I have, at those 2 points, -2 and 3, my derivative is 0, right? So I would like to know what's happening over here to the derivative and what's happening here and what's happening over here. So what I'm going to do is I'm going to draw some dotted lines straight up. And what this does is it partitions the number line into 3 sections, right? It just makes a visual distinction between these 3 regions. And now what I'm going to do is I'm just going to pick a test point. I'm just going to pick any point that I want over here, then any point I want here, and then any point I want here. And I'm going to investigate what's happening to the derivative at those points. Not the original function. I don't care what the original function is doing. I care what the derivative is doing. Because if the derivative is positive, what does that tell me about the original function? It's increasing. And if the derivative is negative, it tells me that the original function is decreasing. So here come my test points. I'll do it in a different color. So I'm going to take a test point, any number I want over here. I like to put little x's. -3. Okay, I'm going to circle it. That's a test point. And now I'm going to pick a point between -2 and 3. A good number between a negative and positive is 0. You don't have to pick 0. You can pick any number you want in there. You have the freedom to pick any number you want. And then any number I want over here, so 4. And I'm going to take these numbers, and I'm trying to figure out what the derivative is doing, right? So I'm going to plug those in.